And welcome back to another PICKit4 and ATTiny how to do it and what can go wrong. Right at the start, I just thought I would download the fuse settings from a brand new untouched ATTiny85 as it came from the supplier. And so we can see the default setting is a 8 meg RC oscillator and the divider is set to 8. So internally the clock runs at 1 meg. So we can go to the low byte settings and we can see here that bit 7 is the clock divided by 8, does what it says on the tin, divides by 8. And it affects the CLKPR register, the clock pre-select register. If this bit is set, it's programmed to a 0, that clock pre-select register will be set to this value, effectively 03 in hex, and that will ensure that the system clock runs 8 times slower than the selected source, and that's what happens at startup. Now if we look at the pre-selector register of the 8 bits, bit 7 is the clock pre-select change enable pin. Sorry, not pin, bit. And then we have the 4 clock pre-selector settings, and you can see here note 1 says the divide by 8 fuse determines the initial value of these bits. If unprogrammed, it's reset to 0, which is divide by 1. If programmed, the 4 bits are set to 0011, giving a factor of 8 at power up. So we go back up and move that over a little bit more. Here we can see the 4 lower bits, the pre-selector bits, and you can see all zeros is a division of 1, so 8 meg clock, 8 meg system clock. And then we go 2, 4, 8, 16, 32, effectively dividing by 2 every time we go up 1. So by the time we get to the divide by 256, with an 8 meg clock, we're running at 31.25 kilohertz, and that will give issues later if you're using the PICKit4, as you will find out. Right, I'll just move this back. Some important bits here. Clock prescaler change enable, the 7th bit. Now this bit must be set high to enable the change of the prescaler bit, but it's only actioned when the other bits in the CLKPR register are simultaneously written to 0. So you have to write 0x80 in hex to the register for it to work. But, the second but, it only stays active for 4 clock cycles. So if you don't change those bits within 4 clock cycles, the enable bit will clear, and when you try and change them, nothing will happen. So this gives us, or it brings us on to this part, which says, you must disable the interrupts when changing the prescaler settings, because if you set it to enable a change and then you get interrupted, when you come back, it will be later than 4 clock cycles, and so your change won't happen. So you should disable interrupts, do the enable, do your change, and then put in interrupts back on. I'll say that again. You set the clock prescaler change enable bit high and all the others low. That puts you into the change mechanism, and then within 4 cycles you change the settings. But interrupts, you must disable interrupts before you enter these 2 procedures so that they follow each other automatically, i.e. there is nothing that can interrupt you setting the bit high and then setting the value, because you only have 4 clock cycles in which to do it. So before you do it, disable interrupts. When you've done it, re-enable interrupts, and then it'll all be happy. Right, so here we have the very simple program I'm going to use. Written in C using the Microchip C compiler. So standard includes, you need the xc.h for the compiler, standard IO and standard lib. I just put them there before I do anything because they're useful. And down here we have a set of defines, basically just to take away these numbers and give them names so you know what they actually mean. So to enable the prescaler changes, it's 0x08, the 7th bit or the 8th bit, depending on whether you start at 1 or 0, is set. And then we have the divider here shown as binary bits so that it's in following with the table. Could have done it as OX, but this just gives you a little more insight into the bit pattern. Right, moving down to the program. Now the program is really simple. It basically loads the enable prescaler changes into the CL/KPR register, and then straight after it, it loads the clock division that you want. Here we have it set to 1, and so basically it's 1 to 1, which if we look back up is all zeros. That would be 8 meg clock running at 8 megs. What I'll do is I'll program that into the chip, which it's doing now, but we're not going to see that. And what I'll do is I'll close this screen down. Right, here we have pulse coming out. That is the time it takes to go from the end of the while loop back to the beginning. And if I just bring in that again, you'll see that after the while loop we go low, we go high, we go low, we finish the while loop, we go back round here, go low, high, low, high, low, high, just to give a series of pulses. And then if we go back and look at the scope, you'll see is that is the time from the end of the while loop that it takes to go back to the beginning, and then we go low, high, low, high, low, high. And so there is the time of when the command was port low, and that's the time when it was port high. And as you can see, it's about 120 nanoseconds, which it reckons is about 8.19 megahertz. And I suppose it should be 8 megs. So if I move that, well, looking at this, I can only get it to 806 megs. So as you can see, 8 meg clock, 1-to-1 divider, and that's what we get. Now if I go back to the program, change it to divide by 2, we'll reprogram the chip, and at some point it changes, and as we can see now, we're about 4 megahertz, and so we are in fact dividing by 2. Well, I won't show you again, but I'll go back and do the divide by 4, program that one in, and of course that should then increase. We may lose lock. No, we've still got a reasonable lock. So let's move the cursor. And we've gone down to 2 megahertz. So we have in fact got a divide by 2. So divide by 4, divide by 8. That should give us the default setting, which should give us a 1 meg or close to 1 meg clock. There it comes in. And there we have it, a 1 meg instruction cycle. The next one we can divide by 16. Cursors, bring the cursors back. So we've got a falling edge. We're close to like 500 kilohertz. So we've halved again. And we do the divide by 32. See if that looks loose. I think it's coming down the pipework now. There we go. Let's move the cursor out. That should be about 250. There we go, 250 kilohertz. So we've divided by 2 again. Next one is divided by 64. It's coming down the pipework again to program, and then we should. Oh, now it's fallen over. Now, if I go back and look at the screen, you'll see nothing changed, but you see we have an error. Now, what's happened there is the PICKit doesn't like the clock speed. The chip is now running too slow for the PICKit4 to program the chip. So if we answer that, it may, no, it didn't change. if we go back to the scope, we will find it hasn't changed. We can get round this a bit by, if we go into the PICKit4 down to communications, this is the speed of the bus. It's running at 125 kilohertz. It needs to be about a quarter of the clock speed. But if we go in and knock that down, it ran, take that away. There we have it. It should be about 125 kilohertz, which it is. We'll try, and that was the 64. We'll try the 128. I won't bother showing it programming on the screen because it's just me clicking a few buttons. We'll watch the scope and see what happens. You'll see it goes a bit crazy as it starts the program. Oh, no, it went in quite well. And that's now showing at 62.5 kilohertz for a clock. Now, what I won't do with this device is, if I go back, bring this one back in. Now, divide by 256 has given me an issue, and currently it bricked the chip. I can't get the PICKit4 to program slow enough, or to do the communication slow enough to recover the 256 clock divider. The system clock is running too slow for the PICKit. So now that device will not, well, I cannot recover it using the PICKit. What I can do is I'll show you what I mean. Right, I've rearranged the screen so you can see the bottom bit here. Now, set it to try and reprogram the divider back to 1, so it should be back to an 8 meg clock. If I hit program button, what will happen? It will try and connect, it will try and erase, then you'll throw this error. Now you can say yes to it, it will keep trying, and then you get this expected 0 got -64. Command has failed to execute on the tool. Programming did not complete. And if you look at what's going on the screen when you program, all sorts of strange things happen on the output pin, but it doesn't like it. It's almost like a bus contention, and I cannot recover that chip using the PICKit4. That's where we got to. Right, well, I've put back in the chip that is running with the 128 clock divisor, and what I'll do, we'll bring this back over to here. I'll change that back to clock divided by 1, and we'll see that with the clock divided by 128, the PICKit doesn't have a problem. Doesn't have a problem programming, and we have in fact got back to roughly, well, we have got back to an 8 meg clock. Yeah, see, back to an 8 meg clock. So, I hope if you found this interesting, you'll want to make some comments about if there's anything else you want to see or any improvements I can make. If you like this video and you wish to subscribe, hit the subscribe button, ping the notify bell, and we'll see you on the next one. Or you may want to comment down below. I think the next video will be on playing with the pulse width modulator registers. So I'll see you next time.